I now want to give some properties of Cauchy sequences. So again, a sequence is Cauchy if the tail end, if I just look at the tail end and I go along the sequence far enough, a sequence is Cauchy if all of the elements are close to each other. They're all within epsilon of each other if I look at the tail end of the sequence. That's not the same as saying it converges to something. Okay, we're going to get to that, but that's not the same as saying it converges. Okay, so if I know all of the terms of the sequence get closer and closer to each other, then that means that by definition that means the sequence is Cauchy. So I'm going to prove that if a sequence converges, then it is Cauchy. So let me just write this statement of the theorem. Hold on. If AK converges sorry, the stylus is really giving me some difficulty. If AK converges to L, where L is a real number, then AK is Cauchy is what I'm trying to write. Okay, let's see if I can continue to try to make this work. Okay, so what is the proof going to be here? Well, the idea, okay, so if I know that all of the AKs are getting closer and closer to L, if all of the AKs are within epsilon of L, this means that the lowest it could be would be L minus epsilon, and the biggest an AK would be L plus epsilon. So this means all of the AKs are within 2 epsilon of each other. Or equivalently, or similarly, or whatever, which is the way I'm actually going to do this, or what I'm actually going to write, if all of the AKs are within epsilon over 2 of L, that means the lowest an AK could be is L minus epsilon over 2. The biggest it could be is L plus epsilon over 2. And so all of the AKs are going to be within this interval of length epsilon around L. So in other words, they're all going to be within epsilon of each other. Okay, so proof, let epsilon be greater than 0. Let epsilon be greater than 0 and choose in so that for all k greater than n, AK minus L is less than epsilon. So if K and L are greater than n, okay, if K and L are greater than n, what I need to show is that AK minus AL is less than epsilon. What I need to show is that this is epsilon over 2. I need to show AK minus AL. I need to show that's less than epsilon over 2. Okay, by the triangle inequality, I'm going to do something in 2 steps that I'm going to do something in 1 step that I've been doing in 2 steps. Let's see if you have trouble following it, pause the video and think about it. That's fine. This is going to be equal to AK minus L, less than or equal to AK minus L plus L minus AL. Now, since K and L are both bigger than n, each one of these is less than epsilon over 2. So this is less than epsilon over 2. This is less than epsilon over 2. So altogether, this AK minus AL is less than epsilon over 2 plus epsilon over 2, which is less than epsilon. I mean, epsilon over 2 plus epsilon over 2 is less than epsilon. Okay, so since ak minus L is less than epsilon over 2 and L minus AL is less than epsilon over 2, their sum is less than epsilon. Okay, so that is the n. We've given an n such that for k and L bigger than n, this is true. Okay, so now I want to prove another thing. If this is a related fact, it's going to use a very similar idea. If AK is Cauchy, then it is bounded. Okay, so what's the idea here? Well, I just know eventually all of the AKs are close to each other. So then, for example, if I look long enough down the sequence, the tail end, all of the AKs are going to be within one of each other. So if k is bigger than n, all of the AKs are going to be within one of each other. In particular, all of the AKs are going to be within one of an plus 1. So now if I look at the front end of the sequence, a1 through an, that has a maximum because it's a finite set, and it has a minimum because it's a finite set. And if I look at the tail end of the sequence, all of those terms are going to be within one of an plus 1. So now the upper bound is going to be the maximum of the first n terms and an plus 1, and the minimum is going to be the minimum of the first n terms and an plus 1 minus 1. I'm not going to write things out completely detailed here. You'll see why I want you to be able to tie some things together. I'm not going to write down every bit of reasoning. One, because I don't want to, and two, because the pen is being very irritating. So choose n. Choose n so large that AK minus AL is less than 1. In other words, take epsilon equals 1 in the definition of Cauchy sequence. Choose n so large that AK minus L is less than 1. For K and L bigger than n. Okay, so what this means is that for all, if I take L equals n plus 1, this means for K bigger than n, I'm going to have the following estimate here. I'm going to have a n plus 1 minus 1 is less than AK is less than a n plus 1 plus 1. So if I look at m, I'm going to say m is the maximum of a1 through an and an plus 1 plus 1, and m is just going to be that same thing but with minimum. Again, it's a finite set, so we know there's a min and max. This pen is really irritating me. I'm sorry to keep complaining about it, but I don't know why it's just not doing what I want it to do. Except it has to be an plus 1 minus 1 because that's the lower bound for the tail end. Okay, so in other words, I'm going to look at the maximum of the front part of the sequence, and then an plus 1 plus 1. This is a bound, an upper bound for the tail end of the sequence. So it means all of the elements of the sequence have to be smaller than m. Similarly, m is the lower bound because it is the minimum of the first part of the sequence, and it is a lower bound for the tail end of the sequence. So these are upper bounds and lower bounds. Is upper bound and lower bound. So in other words, this proves that if I have a Cauchy sequence, it's bounded. Okay, in the next video, we're going to talk about the following fact: if a sequence is a sequence of real numbers, and it is Cauchy, then it converges. Okay, we've already proven in this video that if a sequence converges, then it's Cauchy. Now we're going to prove if a sequence is Cauchy, then it converges. That's a big important theorem that we're going to see, and it's going to be very important. There's exercises in the homework to explain why this is not true if we only look at rational numbers. So the fact that R is complete is going to be important in this proof. Or it's not going to be explicitly in the proof, but it is important, and I'll talk more about that in the next video.